In this video, we will cover the Taylor polynomials and introduction to the Maclaurin series. As a quick overview of what we will learn today, we will construct polynomials using initial conditions. We will approximate functions using polynomials. We will verify our approximations, and we will discuss the difference between Taylor and Maclaurin series. Let's construct the following polynomial given these 5 initial conditions. This is called a fourth order polynomial, and our constant term is called the 0th order. We will first determine the 0th order term by using our initial condition, the function p of 0 equals 5. We take our fourth order polynomial and we plug in 0 for every x value there is. What happens is everything but the constant term goes to 0, and we're left with a naught equaling 5. Now that we've solved the 0th order term, you can see that the a naught has been replaced with 5. Next, we're going to solve this first order term. The first derivative at x equals 0 equals 7. What we'll do is we'll take the derivative of our polynomial, which leaves us with the constant term going to 0 and the first order term going to a constant. After that, we're going to plug in 0 for x and solve for our initial condition. We find a1 equals 7. We have updated our polynomial with our first order term, and now we're going to look at the second order term. We have to take the first derivative again to get our second derivative, and likewise, the linear term becomes our constant, and every other higher order power of x goes to 0 when we're looking at our initial condition. This leaves us with a result of a2 equaling 11 divided by 2. Our third order term requires us to take the third derivative and evaluate it at 0, setting the function equal to 13. The result of this shows that a of 3 is equal to 13 divided by 6. Our last term, the fourth order, requires us to look at the fourth derivative's initial condition. This finally sets x to the fourth power equal to a constant. Therefore, the constant a4 equals 17 divided by 24. Finally, we have our solved polynomial for our initial conditions. Now that we've shown that we can use derivatives to find the constants for polynomial series, let's go ahead and take an actual function, the natural log of 1 plus x, and approximate it to the fourth order. What we will be doing is actually taking derivatives and evaluating it at 0. What we will find is the solutions are our constants, a naught through a to the fourth. For our first term, we are going to set the function itself equal to 0, or more specifically, we're going to evaluate x equaling 0. In this case, the natural log of 1 plus 0 is just the natural log of 1, which itself is 0. That leaves our constant term equaling 0. Our first order term requires us to take the first derivative. The first derivative of the natural log of 1 plus x using the chain rule is 1 divided by 1 plus x. If we then go and plug in 0, we get 1. That tells us that our constant a1 equals 1. For our second order term, we have to take the second derivative. What ends up happening with our chain rule is we pick up a negative 1, and our argument in the denominator gets squared. This reduces down to negative 1. Our third term requires us to take the third derivative. So taking the first derivative of the second derivative brings down a negative 2 Combining that with a -1 gives us a +2 all over 1 plus x to the third, simplifying down to a3 equaling 2. Finally, the fourth term gives us a -3 times 2, allowing us to claim that a4 needs to be -6. So the final approximation for the natural log of 1 plus x is approximately x minus x squared plus 2x cubed minus 6x to the fourth. Now, before we move forward to talk about sine and cosine, I want to return back to our first example. I want to point out what happens to the denominators of our constants. As we go through, we need to take the nth power derivative to solve for that constant. That results in a 1 over n factorial being multiplied by that constant. Finally, I want to talk about how we can approximate trig functions as polynomials. What we'll do is we'll take the first 4 derivatives of sine and evaluate them at 0. So the function itself, sine of 0 is 0, cosine of 0 is 1, negative sine of 0 is 0, the negative cosine of 0 is -1, and the fourth order term is equal to 0. For our polynomial series, we are going to have the repeating order 0, 1, 0, -1, which allows us to approximate sine as x minus x to the third divided by 3 factorial plus 5 to the fifth divided by 5 factorial minus x to the seventh divided by 7 factorial. Notice that sine is an odd function and it only requires odd orders of polynomials to approximate it. I now want to verify the fact that a trig function can be approximated by polynomials. We're using Desmos, and what I've done is I've plotted the graph sine of x. To the left, you'll see that I have created functions from the 1st to 17th order. And we will watch as we add more terms, our approximation will approach the function The first order term, of course, is just a straight line. It does a good job of approximating sine near 0, but falls off the line as we go away from 0. The third order term is just described as the first order term plus the negative of the third order term. When we go and add the fifth, we get a better approximation. And these approximations will continue to improve as we add more terms. So by the 17th order term, we have almost perfectly approximated sine of x on the interval -2 pi to +2 pi. Here are the two definitions for Taylor series and Maclaurin series. The main difference is a Taylor series can be centered around any constant a, where the Maclaurin series is a special case of the Taylor series where a equals 0, or the function is centered about the origin. Here's a list of common Maclaurin series. We have the function 1 divided by 1 minus x, the function 1 divided by 1 plus x, the exponential function, the natural log function of 1 plus x, the trig function sine of x, cosine of x, and the inverse tangent function. Denoted in red is the range for which x can be. The exponential, sine, and cosine are designated that they hold true for all real values of x. Take special care to notice for the natural log, it does not include the number -1, but does include 1. What we learned today is that functions can be approximated by polynomials, and that the Maclaurin series is a special case of the Taylor series.